Hey, so I thought I'd work on this video here. Basically, my life's actually a little bit chaotic right now. It's kind of crazy, and thought making a video would be a little bit cathartic and kind of a break. So basically, I started this a couple weeks ago, and it's in a place where I can present it. Basically, what we have is so in another video, I made this kind of program here, and I'm just going to very briefly explain it now. And basically, what I wanted to do is there's a thing called a Siemens PLC, particularly the 300 and 400 models that use Step 7. They have this certain programming language, and the way the programming and the hardware and stuff works, the programming language is called STL. And so I wanted to use Python to make something that functions the same. And my final result is close. It's not exactly what I would have want, but I spent enough time on it. It's close enough for learning purposes. Basically, as you can see here, it's a little bit hard to read, but all I wanted to do, it's supposed to be a program that calculates G, the gravitational constant for Earth, close to the center of the Earth, like within the atmosphere. So it's G equals 2 times h, which is the height above the Earth, divided by t squared. And in this case, the idea is that someone could use this program that's being written in a very convoluted way to go measure the height and then drop something 3 times, take the average time value, well, actually enter in all 3 time values, and then this will take the average and calculate G based on those. And because of the original project that I did, I used very, very rounded numbers so that everything should be integer based and the final result should be actually 10. And basically what you see here, so this is the program. And to show really quickly, because this looks kind of messy and complicated, the program is actually very simple. This is what the program would look like um, if you wrote it in STL, and actually that's without these longer sentence looking lines, which are actually comments. So these are comments here. Ah. But the rest of it, it's just, L and then a value, T and then an address, L and then a value, T and then an address. And that's how it works. It's very simple. So this is the same thing, but with lots of comments explaining each line. And then over here, I'm tracking what's actually happening in the memory. And I had to do this actually for debugging purposes to get my Python emulator to work properly. So basically, just a simplified explanation. There's a bunch more stuff that I left out, but for this emulator, it includes 2 accumulators, which is true. The PLC does include 2 accumulators, which are like working memory. Um, Then it has, I included several memory addresses where there actually can be many, many, many memory addresses on, and there's different types of memory and all that on an actual PLC. But for this very simple version, I just included 1, 2, 3, 4, 5, 6, 7, 8 memory addresses, and I didn't really define what they can hold, so they can pretty much just hold, whatever size value you want, whatever you would put in there in Python for this purpose here. The same is true for the accumulators, but each of them holds one value is the key. And basically the basic idea of the logic is there's a couple of math instructions which are pretty simple, and then there's basically just 2 different types of move commands. So you have this L here, which which loads whatever is written on the right-hand side into accumulator 1. But before doing that, it moves whatever was already in accumulator 1 into accumulator 2. So it shifts from accumulator 1 to accumulator 2 and then loads the given value into accumulator 1. That's one command. The other command, it transfers whatever's in accumulator 1 into the given memory address. And then the other ones are really, really simple. They're just math. I'll just explain one right here is add. The other ones work the same, but they're like multiply and divide. So add, it takes whatever's in accumulator 1 and accumulator 2, it adds them together, and it restores the result in accumulator 1. So that's how that works. And that's basically all of the functions that I would need to build an emulator for this. So where is my... right here. So this is my program that I made, and it's a lot longer and a lot messier than what I would have liked, and it doesn't quite look at the end, but you'll notice, so this right here is the actual running of the program, and I wanted it to look as close as possible to the code that I had just showed, which is right here. I wanted this to look like this and function like this. But instead of throwing this code into step 7, I guess you could call it an IDE. I don't know if that's technically correct, but it's something like an IDE for the PLC. And instead of throwing this into that and running it either in their built-in simulator or running it on an actual PLC, I want to throw it into my Python emulator and run it there. So that's what I have here. This is the same code. All the hashtag here is just my comments, and it looks mostly the same. I had to have a little bit of differences, and I think the only main differences are, let me get a screenshot of this so I don't have to keep flipping back and forth. Okay, so basically the primary difference for the load command, I had to use parentheses. Same for transfer, I had to use parentheses, but I was able to keep the values the same. So just a number and just MW100, which is a label that you would see in the Step 7 PLC. The other main difference is all the math ones. So in the PLC, it uses like this plus I. I don't know how I can make that symbol work, so instead I used just a label, a method with a name. So my add divide instead of divides I, and so on. Otherwise, you can see it looks pretty much the same. And to make this, first I could show that it works, I guess. So that's good enough. So I already have it written out here. So it works. I had it clear the screen initially. And all of this is just gobbledygook for testing purposes, really. But so basically my memory addresses, um, it's MW100, and then they actually don't go fully in order, but this would be MW100, 110, 120, I think it's 130, 150, 160, 170, and 200. I skipped a couple numbers in there for reasons. So basically, that's the memory locations. And these were just the initialized values that I put in there. Again, just for verification that it was actually working the way I intended. So by the end of it, we should have these values here. And I wrote, this is just text, and then this is the values, and you'll see they match. 21, 2, 3, 2, 40, 4, 10, 21, 2, 3, 2, 40, 4, 10. And then here it prints it again, just again, it was for testing purposes, same exact thing. And so then the final value is actually the MW200 slot, which is right here. And this is correct based on the input values I used, which was 20 for the height, 1, 2, and 3 for the time values. 2 ends up becoming the average time. 40 is actually what you get when you multiply 2 times the height. 4, yeah, I actually can't think of off the top of my head where that, it represents something in the math. I think it was the average time squared. So 2 squared is 4. And then 10 is the 2 times h divided by the average time squared. 40 divided by 4 is 10. And so that's what's going on in here, and that's the final result. And you can kind of see that in my longer tracking here. So this is the change at each step to each accumulator and to each memory address. If you really want to pause and go through that line by line, you can. I'm not going to for the video. Basically now to try to explain some of what's going on here in my unfortunately messy program. It ended up a lot more messy than I wanted. Basically, I had to use object-oriented programming and create a class because, well, I don't know for sure if I had to, but I think I had to in order to make it so that it could look like this, where just like my function, looks pretty close to the way you would actually write it in step 7. The only way I could figure out how to do that and also to change these memory addresses that I pre-hard coded was by using a class. So here's my class. It's just going to create my basically my PLC, set up my PLC. I have my two memory storage locations, one for the two accumulators, one for the different memory addresses that I hard coded, which this makes this not scalable and a pain in the butt, but it works for my little testing purpose here and for a learning project. Because then the only way that I could find to get to both load and transfer functions to work were by actually then hard coding in uh, these cases here for what would normally be called a switch statement, but I don't know what they actually call it in Python. Match case, it looks like. Um, I had to hard code in a value for every single memory word, and typically on a real PLC, you might have thousands, or maybe it's even tens of thousands or hundreds of thousands of these memory addresses. So this is very not practical, making it scalable, but it works for my example here. And basically, what load does, and it looks convoluted, but that's only because I really wanted this just to say MW and the address, but I could keep this simple and have transfer work, or I could keep it simple and have load work, but I wasn't finding a way to make them both work. So basically what happens, this is also another problem that makes it not scalable, or at least it's not ideal, is that my case number, I put a value in there. I could have not used a value, maybe I could just switch that to a string and it wouldn't be a problem. I'm not 100% sure if I can do that easily, but the way that I chose to do it was um, this MW100, which is one of the options here, and the same for all of them. Each of them really just represents an integer. So the problem is if I ever have this actual integer in the program, I think I'm going to run into problems, but um, I picked ones that for this specific example are way outside of what you would actually see. And I could easily make this a really, really large number so that it would not, practically it would not be seen, but it's still not ideal because it still leaves room for bugs and for glitches. But yeah, so basically all it does is if we have a 101 here, which means that we had memory word 100 here, which means that we passed memory word 100 either into transfer or into load, which right now we're looking at load. So it means that we passed memory word 100. Then we're going to do what I said load does. It moves what was in accumulator 1, which is index 0 for my accumulator, into accumulator 2, and then it takes the memory address that we're concerned with and moves it into accumulator 1. And if this is 101, that means it's memory word 100, which means based on the way I laid out the memory up here, it makes it so that we're dealing with index 0. And so on. That's what it does all the way down to the last one. Plus, well, all the way to the last one, except then what happens is, so when we load, if I go back down to load here, sometimes we load an integer, like here we loaded 20. Sometimes we load a memory address, like here we loaded memory word 130. So what I just showed catches all of the memory addresses, memory word 130, 100, and whatever. If we want to catch an actual integer value, then that's where the exception comes in at the end, case unknown command, and then it tells it to literally just, it does everything the same, but instead of using the memory address location, it just uses the integer. It loads the integer into accumulator 1. So transfer basically works the same. But here we don't have to worry about any kind of an extra statement because the transfer can only deal with memory addresses. So we just have our 8 memory addresses that I set up right here. And it's saying that, whichever memory address you have, take and set the memory address of this that represents the class. I don't know how to actually say this right. What happens is this one, so it's taking the accumulator value of the, I guess to say of the class, where you can use the word self, that's the key. So it's taking that accumulator value and it's putting into the memory address that also deals with the word self. Alternatively is I could end up using my specific instance of the class. I don't know if I'm mixing up terms here because I've heard some of this from other programming languages and some of this from Python. But so if like I created this specific instance of my class, my object here as PLC1. And if I only edit the PLC1 values, then I can't pass them back in and edit them through my methods, which is what I want to do. So instead, I pass in this just basically integer that represents my location in memory. And when I pass in that integer, I tell it based on which integer I have, that's uh, which part of the class I want to change, I guess, is maybe how you say that. Anyway, I think it's clear what's going on. I'm just not sure of the right vocabulary to describe it. And then the last three methods that I have here are relatively simple. They gave me a little bit of problems at first, but then they were not so bad to fix once I realized what was going on. And they're just the addition, division, multiplication. They basically all work the same. The addition could look like these. I had a bug earlier, and to fix the bug, I changed this, and I didn't really need to. It didn't actually fix it. I just didn't change it back. So if we look at one of these, which is how I would more think about what's going on, all we do is we take accumulator, which this is accumulator 2, multiply by accumulator 1, and store the new value into accumulator 1. And the same is true for the division and the addition. Um, anything else? So everything from here up is the setup for my PLC emulator. Then all of this is comments and logic and kind of random stuff that it prints out. Maybe we could go down here. That represents my STL code, which looks basically the same. And then this down here is the just the output at the end to tell someone what's going on to verify that it was working, really. Yeah, so that's basically how this works. And my goal was to take an algorithm that is not something that you would use in Python. So for example, if my end goal was just to create, where do I have that at? I think it's right here. So this program was just really to solve this problem, right? Except with this also being the average value for 3 time measurements. Now, really to solve this in Python, it would just take, a line or a few lines of code. But my goal wasn't to just solve it the way you would do it in Python. My goal was to solve it the way I would do it in a step 7 PLC, but using Python. So that was my goal. It was a fun learning project, and I guess that's basically pretty much it. So here's the results again.